momentum thickness. The symbol for momentum thickness is theta. Its definition is the distance by which a surface would have to be moved parallel to itself towards the reference plane in an inviscid fluid stream of velocity u to give the same total momentum as exists between the surface and the reference plane in a real fluid. So to simplify this definition, we could say that we need to give another thickness to make sure that this equation will fulfill the conservation of momentum. So it will depend on the same diagram as we discussed about displacement thickness. We have a thin plate here, thin flat plate here, and then we have free stream velocity, capital U here. And then once this velocity hit the flat plate, the no slip condition occur and it will create a velocity distribution. So previously we already increased its thickness here to fulfill the conservation of mass. Now we need to increase another one thickness here to make sure our calculation will fulfill the conservation of mass. For your information, the displacement thickness, delta star, and momentum thickness, theta, here is the imaginary thickness. Means that this delta star and theta cannot be proved in experimental work. It is just a correction in our equation to make sure that our equation fulfill the conservation of mass and conservation of momentum. So the idea is similar with the previous one. We need to make sure that total momentum in inlet is equal to the total momentum in outlet. So from this diagram, we could say that U here is the total momentum for inlet, and B, C, and D is the total momentum for outlet. To simplify the calculation, we could say that for inlet, so the mass can be calculated by rho, u, and delta, and the velocity is u. So in outlet, we have three areas, and it can be simplified as this. This is the mass for the velocity distribution, and this is the local velocity that acts in the velocity profile. Here, rho u delta is the mass for the rectangular area that have thickness of displacement thickness, and this is the mass for the rectangular area that have thickness of theta. So this is the rectangular area that I said with thickness of delta star, and this is the rectangular area with thickness of theta. Then we need to simplify our calculation. So the basic idea is momentum at inlet must be equal to the momentum at outlet. So the momentum at inlet is rho u delta times u plus momentum for area B, momentum for area C, and momentum for area D. We simplify this one, and then we could find that in this equation, we have theta and delta star. We need to simplify this equation to know what is the equation for theta. However, we have another unknown terms here, which is delta star. To simplify this one, we substitute the delta star here with this equation that we get from the previous calculation. We substitute the value of delta star in here, so we get the term of integral. Then we simplify the terms. we rearrange the terms. We make sure we put the delta here, rho u squared delta as the subject of this equation, and then we could simplify this term into this one. And then finally, we could rearrange this equation, and finally we could say that theta is integral from 0 to delta u over u in bracket 1 minus u over u dy. So as a conclusion, we could say that theta is integral of 0 to delta small u over capital U in bracket 1 minus u over u dy. Theta is the momentum thickness, delta is boundary layer thickness, u is local velocity, and capital U is free stream velocity. Please remember these three equations, delta, delta star, and theta, to make sure that you could answer boundary layer tutorial easily. Thank you. Please subscribe this channel, C23 Classroom channel. Thank you for watching.